Hi, my name is Jesse Hearn, and I will be presenting my time series prediction of dynamic ship system final project for ENME 440. To start off, I performed data preprocessing to fix the time series scaling of the data. The negative 1/20th of a second time value at the first point of each ship simulation was shifted to be the new t equals 0 value, and the rest of the time points were shifted as well to reflect this. Additionally, the time increment of the provided data had time step increments of 0.04999 seconds, rather than the 0.05 second increment that should be expected with a sampling frequency of 20 Hz, and I had to account for this in my model. So in terms of the visualizations that I performed, here's a pair plot of the first 2,000 data points for realization 2 of C state 3. I additionally performed this for the other C states. And this type of plot is apt to show the relationships between the different dimensions, including the relationship between each of the different position and rotation dimensions with time, as well as the different position and rotation dimensions with each other. You can see the time versus position here, and the position versus rotation and such contained within these squiggled lines. So the non-x position plots appear to look like a composition of some sine functions, so these in terms of time here. And then the relationship between some of the dimensions appear as ovular or circular scribbles, such as the z versus rho y plot, seen here. And this is the most ovular in nature. And this relationship between the two dimensions indicates that the ship's bow tips upwards as it is riding upon a wave, and downwards as it descends the wave. Additionally, the area enclosed within the oval represents how difficult it is to rotate the ship about that axis. We see a somewhat similar curve for the y versus rho x plot, as seen here. However, this curve encloses a far smaller area than the previously discussed plot, meaning that the ship experiences far easier rotation about its roll axis than its pitch axis, which makes perfect sense. These relations highlight the presence of intrinsic dimensionality tying the x, y, z, yaw pitch, and roll relations together. This is explained well by the dynamic relationship between the different position dimensions, as they relate to a rigid body traveling on a 2D surface, which is the ocean. I also performed a Fourier transform of the different position dimensions to explore the underlying frequencies involved in their signals. So to looking at the x, as we'd expect, there's just a simple DC offset, no other signals. Looking at the y, we have a DC offset, and additionally, we have a 0 to 0.25 Hertz band, which is full of signals, which correspond to waves at these varying frequencies. And then for the z, we have a similar DC, we have another DC offset, as well as a similar magnitude band of signals between 0 and 0.25 Hertz, again corresponding to waves the ship encountering waves. So for insights from this, again, this is kind of just re-summarizing what I just stated here. And so then if we look to the baseline model, the autoregressive model, I performed an autoregressive model on each of the 3 position dimensions and each of the 3 orientation dimensions. And this is actually a standard model for time series modeling prediction. And this is especially used in stock market prediction and other similar prediction metrics. However, this model fails to account for any interdimensional interactions, as well as all first and second derivative data that was provided with the project. So it's likely going to be limited in its scope and abilities to predict. Cross-validation was performed using a custom time series split for 10 cross-validation elements per realization and using all 8 realizations per C state. So for pre-modeling analysis, I performed an autocorrelation analysis to see if the data was apt for autoregression modeling. And as we can see here, for lag numbers above 10, we actually see performance being consistent. Then for the performance of the baseline model, the autoregression model had high prediction MSEs for a variety of the performance metrics, but low prediction MSEs for others. The ones that were especially high were the Euler prediction MSE for C state 1, the roll MSE for C state 2, and the Euler position, roll, and yaw MSEs for C state 3, with the Euler position MSE being incredibly high at 9 times 10 to the 5th. So we can see the varying performance between the different dimensions, with the yaw MSE for C state 1 being near 0.01, right here, but others such as the Euler position MSE being on the order of 9 times 10 to the 5th, which is incredibly high. This highly variable performance indicates that the autoregression model is unable to account for some wave conditions, causing some predictions to diverge wildly from the ground truth location. This model is better predicting the location of the ship with smaller C state numbers as well, which makes sense because higher C state numbers correspond to rougher, more chaotic sea conditions, which would make location prediction more difficult. So then moving on to our final model, I made a vector autoregression model. And this model type operates similar to the autoregression model, but in addition to accounting for intra-dimensional relationships within each dimension, it also accounts for the interdimensional relationships between each dimension. This ability to account for interdimensional relationships will allow for the model to incorporate all of the dimensions, including the derivative dimensions, into its prediction of the 6 position and orientation dimensions, which should vastly improve its performance over the autoregressive model. Cross-validation was similarly performed using a custom time series split with 10 cross-validation elements per realization, with 8 realizations per C-state. So there was actually a lot more pre-modeling analysis required for the vector autoregression, including the autocorrelation test, which was already performed. Then I performed Granger's causality test and found a p-value of less than 0.05 between all dimensions, rejecting the null hypothesis that past values of each time series dimension do not cause the other series. Then I performed Johansson's co-integration test to establish the connection between all the dimensions, and significance was obtained between all of them. Next, I performed a stationarity check using the augmented Dickey-Fuller test, and the x dimension was the only non-stationary dimension, but it is linear in nature and should not cause problems using this model. Finally, I used the Akaike information criterion to select an order of 34 for the model, and this corresponds to the number of lags that the model looks in the past. This is also, in order to get an accurate comparison, I used the same order for the autoregression model. So for the final model performance, we can see that all the values are actually relatively low compared to the autoregressive model, which we'll get to on the next slide here. So we can see that the average time in seconds to deviate 1 meter sphere from ground truth was vastly improved for the vector autoregression, as well as the MSEs in general. So including especially the Euler distance MSE, which while it's still high at 18.8, it's much, much less than the 9 times 10 to the 5th magnitude that we saw before on the autoregression model. So overall, we see relatively stable performance between the different dimensions, with something like the yaw MSE for C-state 1 being less than 0.01, even improving upon the incredibly small one we saw for the autoregressive model. And the Euler distance MSE for C-state 3 was trimmed down to be less than 19 from that 9 times 10 to the 5th value. The stable performance indicates that the vector autoregressive model is capable of accounting for most wave conditions, and this is due to the vector autoregressive model being able to account for the interactions between dimensions, which is what we predicted previously. And this ability is likely the cause of its improved performance over the autoregressive model. And like the autoregressive model, the vector autoregressive model was better at predicting the location of the ship with smaller C-state numbers, as we see here. The average time it takes in seconds to deviate 1 meter sphere from ground truth decreases as the C-state increases and the waves get more chaotic. So overall insights. This problem has its own unique challenges due to being a time series data set. The ideal solution the ideal modeling solution accounts for the temporal dependency and high autocorrelation, which makes both autoregression and vector autoregression models apt for use in this program, or in this problem. But the vector autoregression is obviously better because it accounts for the interactions between all the different dimensions. Pre-processing the data was insignificant, and it may be possible to actually get away with not pre-processing the data at all, just sticking with the negative time value and and assuming that the 0.04999 value is 0.05. But I haven't tested this. The VAR model was also a far more effective model than the autoregressive model. For this data set, and produced both higher accuracy and precision for the majority of evaluation criteria, as we saw in our performance comparison slide. So in terms of future directions for this project, the next model type to try would be actually an LSTM, or long short-term memory recurrent neural network with the data using Keras. LSTM networks are capable of handling multivariate time series forecasting problems, and with the right hyperparameters may allow for better performance than the VRR model. However, tuning these hyperparameters will be the majority of the resources sunk into this modeling exercise. Future models could also introduce physics-informed penalty terms integrating the equations of motion of the ship system. The equations of motion of the ship system would be educated by the ship form and mass characteristics, and these physics-informed penalty terms would penalize any model which differs from the predicted equations of ship motion, leading to an explicit tying of the different position and orientation dimensions together, allowing improved model performance so long as the assumed equations of motion are correct, which, however, may be difficult. So in terms of guidance for future students, you should start by pair plotting the data to get a visualization of the interdimensional effects, as well as the summed sign nature of the underlying data. This is more than enough to understand the basic patterns underlying the data. Thank you.